So in this clip, we have two quick results about null spaces of powers of t. So if we apply t again and again, so we iterate applications of it, the first result is that the null spaces of these iterates of t can only increase. The second result is that if it ever stops increasing, then it never increases again. So it just stays at that same fixed vector space from here on in. So more precisely, if t is an operator, then the null space of t naught, which is the identity, is contained in the null space of t, which is contained in the null space of t squared, and so on and so forth. And so the proof of this one is super short and sweet. If we take v to be in the null space of some tk, then if we have tk plus 1 now applied to v, then this is going to be t applied to tkv. But we chose v to be in the null space of tk, so then that's going to be t of 0. So this is by choice of v in the null space there. And then linear maps always take 0 to 0. And so this tells us that tk plus 1 also is going to kill v. And now reading from right to left, we have that the null space of tk is contained in the null space of tk plus 1. So that's it. Super easy. Okay, for the next observation, we have that if you ever get to a point where the t to the m plus first null space is equal to the t to the m null space, then when you go up to t to the m plus 2 or m plus 3 or m plus 4, it's always the same. It never grows anymore. So if it stops at some point, it stays stopped. And then in the next clip, we'll prove a little result that says it stops at some point. So let's see. So by 8.2, we already have one direction. We know that these things are always increasing. So now we just need to show that the reverse inequality holds after some point. So it suffices to show that the null space of t to the m plus k plus 1 is contained in the null space of t to the m plus k. So in other words, after we're out past the mth one where it stopped, we can back up one, and then hence we can back up as many as we want by iterating the process. So in order to start this off, suppose we have an element v in the null space of t to the m plus k plus 1. Okay. So, and then the argument goes very much like we had in the previous result. So you just split powers of t. So this is equal to 0 on the one hand, and on the other hand, yeah, actually here, let's do the little thing where we leave a 0 out there in front. And so then this is t to the m plus 1 applied to t to the k applied to v. And then that tells us that tkv is in the null space of t to the m plus 1. And that one, however, is by hypothesis the null space of t to the m. And so now we have tkv in the null space of t to the m, which means that tm tkv equals 0. And that last one there is telling you that v is in the null space of t to the m plus k. So we were able to go from the null space of the m plus k plus 1 down to the null space of the m plus k, so we can do that backward step. And that gives it to us.